Now, the adoption in those days of 802.11a is a little bit slow because, again, it's a new band, so people don't want to get rid of everything they have to buy entirely new equipment. So at the same time as 802.11a is published, the IEEE tries to bring the same kind of efficiency in a band that people are already using, 2.4 gigahertz. And they finally come up in 2003 with basically 802.11a implementation brought into the 2.4 gigahertz band. And that amendment is called 802.11g. So it's still FDM with still the same rates up to 54 megabit per second and still the same BPSK, QPSK, 16 QAM, 64 QAM. You can think it as 802.11a in 2.4, no more than that. It took some time for this amendment to come after 802.11a because there are also some power issues. Power and also coexistence issues with 11b and 802.11. So it was just not a matter of putting 802.11 and scratching 5 gigahertz in there to put 2.4. There were a little bit more tasks to be done to make it possible in 2.4 gigahertz. Because you have to be able to have new speeds, but you also have to be able to make sure that what you bring into the amendment is not going to be disruptive or destructive for what is already out there and working. So this backward compatibility with 11 and 11b is key to the success of 11G. All right, downsides of 11G? Well, you are still in 2.4 gigahertz, so you still have only 3 non-overlapping channels. We said in some places you could use 4, but if you think of the 25 megahertz separation of 802.11, that's only 3 everywhere in the world. Plus, it's still the ISM band, which means that basically many other devices are going to be there sending radio waves that are going to disrupt your communication. So it's not ideal. But the good thing is that you have here devices that already exist and that you can bring to the market with new speeds that are not going to be mandating new hardware for the clients and for the access points. You can just bring new access points that will be bringing that speed and that will still be compatible with the older and already existing hardware you have. So that's a big plus. Now, if you bring 802.11g to the game, what kind of distance do you get now? All right, still the same thing as usual. Depends on the power, depends on the client, but in those days they still try to give you some values. So because it's backward compatible, in theory, your device, if it's 11G, it must also be 802.11b and 802.11. As a matter of fact, the first sentence of the 802.11g amendment is that this is an extension to 802.11b. So something that is 11G should be able to do 11b and 802.11. And of course, your device is going to choose the fastest speed it can based on the distance and the signal quality to the access point. So in theory, if you're very close to the access point, you get 11G speed. And as you move away from the access point, you downgrade your speed to a point where, well, you have to choose something that is not OFDM anymore, but that is still something that is fast. So you revert to 11 megabit per second. And then as you move away, you go back to CCK 5.5 and then DSSS 2 and 1 megabit per second. So that's the theory, right? You would slow down as you move away from the access point. In practice, it's not exactly how things work. And the reason why is because each of these data rates, each of these speeds require you to have a certain SNR and a certain RSSI. And the RSSI you need for 11 megabit per second may not necessarily be less than what you need for 12 megabit per second or vice versa. Which means that, in fact, if you take into account not only the RSSI, but also the SNR, but also the powers that are allowed for both the amendments, the distances you get are, in fact, a little bit different. The thing is, because the 802.11g amendment uses OFDM, and because you have those mini waves next to one another, you cannot be as powerful as you would be with 11b. Because it's not one big wave, it's plenty of mini tiny waves. And if you were as powerful, you would not be able to distinguish one tone from the other. So when you use OFDM, typically you have to reduce the power a little bit to still maintain this distinction. There are also more complexities in the way the signal is formed that make this power reduction mandatory, but it's not necessary to go there for now. What matters is that OFDM offers better resistance to interferences, but you also communicate with lower power. And these are the powers that are allowed in these different amendments. As you can tell, the 802.11g protocol is actually much, much lower in power than DSSS, from 20 dBm to 15 dBm. And as you remember, 3 dB is twice the power. So here you're almost 4 times less powerful when you're at max power with 11G than when you are with 11B. So of course that is going to affect the range. So in practice, when you are in that 2.4 GHz band and you have B, G all together, you're going to have some rates that are going to be very fast close to the access points, and those are of course going to be OFDM. But as you move away from the access point, at some point, in fact, you're going to jump way before you think to OFDM rates and continue going down to OFDM rates before you actually reach the point where you have to use DSSS. And that's because the SSS is much more powerful. So the area where you would reach 11 megabit per second would be behind the area where you would have 6 megabit per second. And then of course, as you move away again, you'll drop to 5.5 and 2 and 1. All right, so what kind of distance does that make? Well, again, depends very much on the power, depends very much on the client, but same client, same access point, rubber duck antenna, max power, these are the distances they were communicating in those days. Again, do not take them as absolute values because today depends very much on what hardware you're using as a client, and it depends also very much on the access point quality you have. Many access points can do much better than that with a good client. Some access points can do much less than that. And also keep in mind that it's not because you can have those ranges that your client is going to use those modulations at that distance. So for example, if you look at the 6 megabit per second OFDM rate, you can get something around 100 meters or so at that speed. But does that make that your device will choose to use 6 megabit per second, where at that distance it can also use 11 megabit per second? Not necessarily. It depends entirely on how the algorithm is implemented in your client. Some drivers will just go down the list, OFDM and then DSSS. Some others will say, I'm just looking at the data rate. If at any given distance I can get a better data rate with another modulation, like CCK, I'm going to use it. And I will be reverting to OFDM only if I don't have a choice. But then at that point where you will have to revert to 6 megabit per second OFDM, you can probably use another modulation that is faster. And by the time you cannot use that faster modulation, it's too far for you to use 6 megabit per second anyway. So some devices will result in never using stuff like 9 megabit per second or 6 megabit per second because they can use 11 or 5. So that is very much dependent on your hardware. So the basic rule is it's more complicated than it looks. In theory, as you move away from DAP, you slow down. What distance can you get? It depends very much on your client, depends very much on the environment, and it depends very much on the algorithm implementation in your client. Okay, so that's about the distance. Another thing that the 802.11 working group had to take into account is what we call coexistence, because you bring 802.11g in a world where devices are 802.11 and 802.11b, and those have to coexist. Coexist means that 802.11g devices are going to send frames using OFDM, and the existing 802.11 or 11b devices are not going to understand OFDM frames. So what happens? That's a problem, because if you just send your frame using OFDM rates, what's going to happen is that the 11G device is going to fill the air, wait at the IFS, count down, get to 0, and send a frame. And of course, the range of that frame is going to reach the 802.11b device that is not going to recognize that 11G communication OFDM. So that B device is going to hear some things, but it's going to think it's just noise because it does not recognize OFDM. And the result is that that B device may think the air is free. There is no 802.11 transmission, and it may be communicating at that time, and of course that creates collisions. So how do you solve that? Well, the idea of the 802.11 working group was to say, what we're going to do is when an 802.11g device detects that there is an 802.11b device in the cell, or 802.11 for that matter, the 11G device is going to tell at B speed, I am going to send a frame, and that's going to use RTS-CTS. Remember RTS-CTS? Request to send and clear to send. So that communication is going to occur first. And the good thing is, because it's being sent at B speed, the B device is going to hear and understand the question. And the RTS-CTS exchange is also going to mention the duration of the G exchange that is going to follow. Pretty much that way. The G device is here, the B device is on the left, the AP is on the right. The G device says, I am going to send for this duration, for example, 3.2 milliseconds, and it says that at B speed. So the AP replies, okay, I'm hearing you, you're going to send at that speed for that duration. So the B device does not understand what follows, that G communication that you see here on the screen. But it hears that somebody was supposed to be sending for 3.2 milliseconds. So what it does is that it resets its nav, network allocation vector, to be silent for 3.2 milliseconds more. And that allows the G communication to occur without any communication issue. You can use, in those days, the clear to send, request to send exchange. You can also use what we call a CTS to self, where the client just says, I'm okay because I'm going to send for that duration. In those days, it's seen that RTS, CTS is a cleaner way of doing it. CTS is a shorter way where the station just allows itself to do it, but the game is to advertise to the B client that you're going to communicate. But there's also a question of range. We know that the AP is heard by everybody, so it's better to have the AP reply with a CTS than to have the station reply to itself with a CTS, where the B station may be too far to hear that message. So both systems are used, but RTS, CTS is seen to be a cleaner way of doing things. Does that work well? Yeah, that works well because you have that protection against B client communication. And as soon as there is a B in the cell, use this system and you avoid collisions. The issue though is that when you do so, you're wasting an enormous amount of time. So that is a good protection for the B clients, but for the G clients, that's a nightmare. Why is that? Well, because suppose you have your devices here again. As soon as you want to communicate and you're close to the access point, you can count down, send your frame, and if you're close to the AP, you can send at 54 megabits per second. Of course, you know now that you have to acknowledge each frame. There are some silences between frames, etc. So 54 megabits per second is the speed at which you send your frame. But if you want to talk about throughput, the average download speed you can get, for example, you have, of course, less than that. If you're one single station in an access point cell, all by yourself, close to the AP, and you talk at 54 megabits per second, you can expect a throughput of about 23, 24 megabits per second. That's if you're all by yourself. Now, if you bring one B client and you start introducing this RTS, CTS mechanism that has to occur before you send those frames at 54 megabits per second, you waste so much time that suddenly your real throughput, even if you communicate at 54 megabits per second, falls down to something around 8 megabits per second. You waste so much time saying that you're going to communicate that you don't spend that much time communicating anymore. And that's just one B client being here, right? The B client is not sending anything, it's just there. And because it's there, you have to protect yourself against possible collisions. The issue with that mechanism of protection is that it's something that gets contaminated from one access point to the other. The way it works is that as soon as there is one device associated to the BSA, that's how the 802.11 standard says it, the access point has to advertise that there is one B client associated to the BSA and that you have to use protection. But most vendors say, what do you mean associated? Really associated, like having an association ID to the access point, etc., or just there? Because if that client is just there, even if it's not associated yet, it may be sending traffic, probe request, etc. So we need to protect as soon as we detect that device. Associated means just being present, not necessarily associated to the access point. So most vendors have an extended understanding of what associated is supposed to be. And the result is that as soon as there is a B client in the area, the AP is going to inform the clients that there is a B client and that we have to use protection. And it does it in two ways. The first one is in the beacons, the access point is going to mention that there is a B client present. That's one bit in the beacon. And the second bit is going to say, you have to use protection. So you have the G client, you have the access point here, a B client comes in, and suddenly the AP starts saying in the beacons, there is a non-G client, it's called non-ERP, that's the technical name for non-G clients, that's 11B. There is a non-ERP client in my cell, yes. You need to use protection, yes as well. Those two bits get set to 1. So as soon as you have that, G clients start wasting that time using the RTS, CTS. So that's one issue, but the second issue is that that awareness gets a contaminated transmission from one AP to the other. What that means is that if you have one AP that starts advertising that it sees non-B clients and that protection needs to be used, well, the neighboring AP that's hearing that neighboring access point message is going to think, I don't see any B client myself. But maybe that B client my neighbor is reporting is somewhere between my neighbor and myself. So I'd better have my client use protection just in case they would be in that area so that they do not collide with that guy that I'm not hearing myself. So you have a wave of non-ERP, no, but use protection anyway, yes, messages that spread from one access point to the next access point. And before you know it, your entire floor, your entire network uses protection. Even if there is only one B client somewhere in the corner of the building that is not even associated to any access point. So you see, it's not very efficient.